So, hello everyone, good morning. As usual, I will start by repetition or review for what we have done so far. I don't know, I need to repeat this because maybe I found some students confused on this. So, we said that in our procedure, we divide our work to steps. So we have step 1. Can you remind me what we do in step 1? Okay. We try to match PSAT. I will mention this also in each step. So, So in this step, what's the average absolute error should be in this step? Around 1 or below 1%. So we will see. Is this clear now? So in step 2, what we will try to do in step 2, PSAT and CCE. And when we say PSAT, it means bubble point and oil density at bubble point. So what's the average absolute error now for those both together? 1%. The same. You see, that's why I repeat this. Yeah. In step 3, I don't need to. What we will try in step 3, we will also try to match PSAT, CCE, and now we will add DLE. What's the average absolute error for all of them together? Below 5%. And now the last step, PSAT, CCE, DLE, and Separator test. Also below 5%. And when I say below 5%, for all of them, if you have, for example, this is 2%, 3%, 4%, then you are okay. If you have, for example, here 2%, 3%, 7%, 12%, this is not good. You need to fix this stuff. So we will talk. Last time we talked already about this step. You remember we tried to match DLE and we repeated that again. This step is the most difficult step. This the third one. The better the match here, the easier will be here. Because here in Separator you will need just to match a few points. So this step it's the longest step in terms of time. You need to pay a lot of time here. And once you achieve the best results, maybe you achieve something. Maybe you achieve 4% and you say, okay, I can improve that. If you say, okay, let's say what I mean here exactly. If you achieve 4%, you say, okay, I am below 5%. So now I will go to this stage. You will find it's difficult to stay below 5% here. It's very difficult. So what your duty here is not to, it's acceptable to be below 5%, but if you say, okay, if I achieve 5% or 4%, I will go to this step, maybe you cannot achieve 5% also here. So that's why we say this is the most difficult step. You need not to achieve below 5%, you need to achieve the lowest percent you could. However, it's acceptable to be 4%, but the question now, are you able to have below 5% also here in this step? This is the question. Because if you could not achieve this, then that means you go back. And maybe you go back even from the first step, if you could not achieve this at the end. So now, your duty will be exactly to have, even if you could, 1% here. I don't know, is there anyone who could achieve something like this, or 2%? I mean, do you achieve a lower than 5, or you just say, okay, I achieved 5, then that's okay for me? So if you achieve 1 now, today, it will be easier for you to stay below 5%. Yeah, this is the first step. So we say average absolute error. I have seen this in many reports. You need to perform this at before and after each step. Remember that. In your report, I have seen that some students start to try to talk about matching without evaluation. So the first step, even before matching PSAT, the first step is to see what the average absolute error for the equation of state before matching. So then you say, okay, I have 10% error, then I will try to match PSAT. After this step, it's something like this. You start from here, you evaluate, and then you calculate PSAT. And then you go back again here. And you calculate here, and you go back here, and so on. So before and after, this step is repeated before and after each step. So average absolute error is calculated always before and after your current step. Is that clear? Okay. So to me, I have tried to match the DLE data, and now I will start by before starting separator test. As I've said before, you need to evaluate your step before and after each procedure. So now we are in this step, and I will see now what's the average absolute error before I go to this step. So I just go to, I want to start by evaluating PSAT. So I have the saturation pressure and oil density at saturation pressure. So this is the lab data, and this is equation of state. Now I will copy paste here. So this is the first step. The second one will be CCE. Make sure that you always check which model you deal with. So here we are dealing with the last one. So this is the relative volume, and Okay. I will put it here, then I need to sort it. So, yeah. And now in differential liberation. So we have oil density. Yeah, I think I have already done this. So before I go to separator test, now I have in DLE data, I have 4% for GOR. And this is 3, 2, 1, 2, and this is, you can see, below 1, and this is 2. So in all of them, I am below 5%. Today we will try to add our separator test data. This is correct. I need to edit this. So, and then we will compare what's the average absolute error before matching. So let's see our report. So this is the separator. This is the separator data, and we have all of them 2 stages. What does it mean 2 stages? We go from bubble point to this pressure, and then from this pressure to this atmospheric pressure. So this is 2 stage, 2 stage, 2 stage, 2 stage, or 2 stages. So how can we evaluate this data before we start? This is lab data, and we performed different measurements, or the same measurement at different conditions. So which one is the best for you? First of all, why we do this? Separator test. We do this to find the optimum condition for my fluid. What does it mean, the optimum condition? The condition that will keep or give you the highest oil volume and the lowest gas oil ratio, because you will try to make your liquid phase with the largest volume, because we are selling liquid. So taking the gas from liquid means you lose some money at the end. So what's your choice will be always the lowest GOR, the lowest GOR, the lowest beta O, and the highest ABR. The lowest GOR and the lowest beta O, and the highest ABR. The lowest beta O will mean that your oil will not shrink a lot. So it will shrink in, small. And the highest API, as you already know, that the highest API will give you the highest price. And your oil, it means more light or lighter. So that's why so according to these experiments, the second stage will be your optimum stage. So the optimum stage is this one, because it gives the highest API and the lowest beta O and the lowest GOR. But what we will try to do today, as you can see in the first step, we will try to define these conditions in the equation of state, and we will try to simulate each condition. And we will compare them together and to see, is my equation of state model is able to give me the optimum case as lab data, which is the second one. And this is the first step. So just as usual, when we want to simulate an experiment, we go to these bottoms here, which are the equation of state calculations. So for separator test, today we will use this one. So make sure that you choose your model, and we are sure here we have a model with below 5%. We can go to this step, but for me, in my model, I think I have 4%, and maybe I will not be able to achieve 5% in this step. That's why you need to pay a lot of time in this step to minimize your average absolute error to be able to stay below 5% in this step. So now we will enter the first stage according to PVT data. And the first stage, the temperature is constant, but here we go from 50 to 0. I've already prepared this data in this sheet, so I can just copy paste and calc. And the software will give you the oil density, which I mean the most important things you need here is oil density from equation of state and oil formation volume factor and gas oil ratio. And here there is a big question. What's oil formation volume factor here? Because if you compare this with your data, we have two formation volume factors. We have this one, and we have separator formation volume factor. What's the difference between this and this? Here, in this one, in two stages, we go from the bottle point pressure to the stock tank power condition. But here, we go from the separator stage, from the specified condition. So that's why we have this for this condition and this for this condition. But here we have only one because we go from bubble point to atmospheric pressure. So which one we want to match in the separator test? Is it this one or those two? Yeah, the second one. So now we calculated the data, and we will copy this data so maybe you don't need this. So I did this for the first stage. I just entered, and now you need to change only this number. 15, change it to 100, then copy oil density, oil formation volume factor, and gas oil ratio. So the same, just change this number and calc again. And make sure that you copy the oil density from your equation statement from the correlation. They put this just to make a comparison. So now your equation of state is not able to produce the same number. However, maybe you evaluate this by average absolute error to know what's the error between this and that. So in this second stage, now we are in 200. So So now, I think you need some time to finish this. So you don't need to repeat the last steps because they are already here. You don't need to re-evaluate the PSAT and they are already performed. And now what you need, you will need to use this slide to copy the data from according to your equation of state model to here and to see which one is the optimum case or the optimum condition according to your equation of state model. So here, according to the equation of state model, we see that here we have the lowest oil formation volume factor. So it means that the optimum condition is the first one. However, in the gas oil ratio, the lowest one was in the second condition. So equation of state does not give reliable results. It gives at the same time two optimum conditions. Because the optimum condition should have the lowest beta O and the lowest GOR in the same condition. But we found the lowest GOR was in the second condition and the lowest beta O was in the first condition. So it says like this one is optimum and this one is optimum. And that's wrong. So now what we will do, we will say, okay, our equation of state is not able to predict the optimum condition as lab data. This is lab measure. You see here, in the second case, you have the lowest GOR. So this is the lowest value if you compare it with this and this and this. This is the lowest one. And here, it is the lowest beta O. So if you compare this with those, here you have the lowest beta O. And the highest ABR. So here's the highest one, and all the others are below this value. So you can see clearly that your optimum case is this one, the second one. Your equation of state says, okay, if I equation of state says that your optimum case according to GOR is the second one. And it says also at the same time, the first one according to beta O is the optimum case. So your equation of state model is not able to produce the optimum case as lab data. And that's because your equation of state is not valid yet. So that's why we have step 4. And now what we will do, we'll try to match separator data. And okay, now there's a question. I will match separator data. Which data I should match here? All of them, or one of them, or what? Yeah, exactly. We will need to match the best condition, the optimum condition. Because this is the condition that we are interested in. So we want our equation of state is able to produce the same readings of the optimum condition. So here, separator test, we can add something. Here we say optimum. So in separator data, we have It's not like in DLE or CCE or BSAT. Here you have different conditions, and you have to choose one of them. And here we choose the optimum because we want to match this data here. This one. And this is will be your according to PVT experiment. This is your choice. So you will build the separators which contain this condition. So that's why now we want to match these data. So I hope that you have finished it. This one. This is two stages. Yeah. How you know? Because it comes this one. Okay. From here, this, you have pressure and temperature, and you have this amount of gas. From where this gas comes? Because you have a first stage. The first stage it is from the bubble point to this pressure. So that's why it's not written usually. It's not written. You don't need it. We always start from bubble point in separator test. And Professor Ganzel showed that here. So from bubble point to 50 psi gauge, and from bubble point to 100 psi gauge. This is the first stage. From bubble point to this condition, this is the first stage, and the second stage to the surface condition. This is all of them 2 stages. Maybe someone can ask a question: why we have 2 stages? Why not 3 stages? Actually, the more stages you have, the more liquid you will have at the end. It's like the example Professor Ganzel says to you. You open the bottle slowly. So we wish to have maybe 100 stages if we could, but that costs a lot of money. So that's why we say 2 stages, because the company will say this is the maximum stages. I cannot pay for you more stages. We cannot. But theoretically, the more stages you have, the more liquid you will have in stock tank water. So I hope that you have finished this step, and now we will try to enter lab data for the separator test. And you know already that when we enter lab data, we go to this, and this time we go to SEP, which is separator. So now, according to lab data, we have gas oil ratio. This one, I have to edit the pressure condition. Here should be 100. And here.
Did you see that? Yeah, I can, but I don't know if
So now you can press OK. And now we go to simulate the same condition, and we will compare between the calculated data and measured data. So we go back here. Yeah, I have. So you can see that when we evaluate the equation state, we found it's okay for beta O, but for RS gas oil ratio, I want to make sure from okay we are oh okay 1 moment please. Yeah, now it's okay. So we have 10% error here. So make sure this is your optimum condition according to my entered data here. This is the optimum condition. Yeah, that's correct. And so now I've reviewed this and I saw that I have 10% here. So I have focused on this. I have not done any tuning before I evaluate my equation of state. So now I know that beta O is already matching. So what this will tell me, it tells that you don't need to include this in matching separator data. When you match this data, DLE, this will already be matching. So why we have a low percent here? Because we matched this data, and when we match beta O here, we have that leads to have a low percentage of error here. However, if you remember that when we match this, we took only the first point. So you see now we keep this procedure very simple. We match it only this point, and that leads to match all data here and the separator data here. So that's why we say it doesn't mean if you input a lot of measured data and use it in tuning, you will have the best results. It's not like this. You remember last week we say that your golden rule should be to have the fewest points and the most important points. So here you always take the data at saturation pressure. This is the most important data for you. And maybe you include the points at the very end of your measure. So I take the first point and the last point, and then I compare which results are better for me. So now we know when we took this point here, beta O at saturation pressure, we could have a low absolute average error in all data here and also for the separator. So now keeping this point matched will preserve my matching here and here. So now I don't need to keep this process more complicated to include this in matching. Because if you match this, maybe you shift a lot of other points. So now that's why you need to evaluate before you start tuning. At each step, in step 1, don't do tuning. You start by calculating average absolute error. Then you start step 1. Then you go back to average absolute error. Then you go to step 2, and then you go back, and so on. So this is the way. So now I found that this is already matched. I will not include this in tuning. I found this not matched. So now I will include this, and the question will remain. If I include this, do I need to keep this or not? Because here I have, this is, this is related from the separator test and the DLE. They are related to each other. So if we include this in tuning, do we need to keep this or not? This is depends. You will try to test this. So I will say, in my opinion, I will say, okay, I will include this in my tuning first thing, and then I will ignore this. And let's see what will happen. If I achieve lower matching here, and this one is shifted, then that means I will need to keep both of them. And okay, maybe someone thinks in another way. He says, okay, I will take only this and ignore all the others. And we tried this last week. We found when you take the worst thing in your tuning and try to match the other data, then you will match this and shift all the others. So now we will say, I don't know, I have not tried that at home. This is will be your task before you receive your term project. I will not require any report for this. However, if you do this and you need comments, I will be happy to do that. That will help you on your term project. So maybe it takes time from you, but at least do it for 1 hour or 2 hours. Try to do that. So as usual, when we do tuning, we go to this one here, this bottom, and okay, here we have all the lab data. Yeah. And maybe now the process is more complicated. So before we used this model, which is the simplest one. We use only the TC/PC eccentric factor. Maybe now you need to go to here. You know what's the difference between the first and the third? In the first one, we are talking about TC/PC eccentric factor. But in the third one, we are including omega A, omega B. And maybe someone says, if I include more parameters, the problem or the tuning will be easier. That's not always the case. Maybe you include other parameters, and then you found the results get worse. So I will not start by this. Always start by the simplest approach and evaluate. Are you able to do something or not? So before, as we usually do, before we play with this model, let's copy it and try to do that in a separated mode. And I will call this file separated. So now I have to review. We say, okay, we need to keep this matched with the highest weight. What about this? Okay, we usually get 5 or medium weight for oil density. I think that's already mentioned here. Don't forget to assign it's the same which was written in the last assignment. So now we will try to assign weights to GOR and oil formation volume factor. So here we want to give the low for both of them. We say volume, anything related to volume, we use low weighting factor. So low, what does it mean? It means from 1 to 3. It's 10 in text PVT box, but here you may choose 1, 2, 3, and here the same. If you start by 1, maybe next step you try 2, and so on. So you change in this, you move on with these numbers until you get the match. So maybe I will start with the lowest weight. For both of them. I've already said I will not include this. I will exclude this. So now I will exclude the oil formation volume factor. And what we have added here is just another 2 points. So now we have 2 points here, which is for GOR, which are for those points here. So we have 2 points here. In DLE we have 2 points also. And here we ignore all of this. We don't have any pointers. And here we have 2 points. So in general we have 6 points. And why we excluded CCE? You don't like questions. Yeah. What?
Before the separator.
Yeah, in DLE last step we say we don't need to match CCE, even from here, in this step. It's already matched, but how it is matched? We know from volume shift, but which property was used to match this step? Exactly, oil density at saturation pressure. So you know, oil density, it's mass over volume. And for the volume, it's fixed by volume shift. So that's why when we fix this, all of data here is fixed. So now we will continue with the same way, with the same technique. We will not include this because we already know if we match this, then we will match this indirectly. So you will know this when you evaluate your data. So how we could know this? When we calculate the average absolute error. So now, any time you found that something is already matched, it means like it is matched indirectly by other measurement. So that's why when we matched this, we found this is matched. But you have to determine which one is the main objective for me, and which is the second objective. So it is matched indirectly by other property. So here, relative volume, it's matched by matching oil density. So we will not include this. Any time when we do regression, so anytime we choose this one here, we will not choose this from here. And we need to choose both of them. So now, we say this is our first choice. And what about the separator? For the separator, we need to match this. We found this has a very high average absolute error, 10%. So we will include this. We will not include this. Why? Because we found. Okay, we exclude it. It doesn't appear here. So if I include it from here, Yeah, it will appear. So I will not include this. As you found, if I include it from lab data, you still have the choice to include or exclude them. So I usually start from here. I exclude my points from here, from this point. Okay, I will choose the first one, the second one, and GOR, then this point here. For this one, I found that when I match this one is still off. So now I will take the reverse of this. I will take this one and I will see if I match this one, is this improvement or not? Maybe this is the main objective. It's the same what happened with oil density. So we will start with this, and I will not go to omega A, omega B. I will still use the same approach. Okay. Medium. Okay. So maybe because I have choose some settings, I will copy this also. And now I will try with TC, PC, volume shift. I will choose all the pseudo components. This is my settings. Remember that before we have chosen a small range for our regression. Oh, still, yes, maybe we need it. Yeah. So remember that before we chose this last exercise. In this step, to get the match, maybe you need to increase. If you are not able to get the match, then maybe you increase this. However, we said we made this range small because it's easier to get the match in this way. If you increase this range because you could not achieve the match, then that's a good choice for you. You give your parameters more region to get the match. Okay. So now we will try to, and we found that there is improvement here. I'm sorry because I'm taking your time. It's already 12 o'clock, but we need maybe from 5 to 10 minutes more. So I will not keep waiting this. Oh, still improving. So now we can compare. We have 5 points here. Okay. Saturation pressure intensity. Yeah. We exclude GR from DLE. So we have 5 points now. 5 points, and you see here we could match this, and I think there is a good results here. We will compare them in terms of average absolute error. So we will start by DSAT. So for DSAT, it's still CCE. No. So we keep this matched, and for the density it's okay. It's still below 5%. Let's compare the other. What about CCE? If we take the relative volume, whoa, what's this? So now we still have a no error here. So we say okay here, okay here. Let's see what happened with DLE and separator test. Are we in the okay range or not? So differential. I go back, start with oil density, oil formation volume factor, GOR, Z factor, and oil viscosity. So for DLE, it's still okay. Oh, it's not still okay. You see, we have chosen the same one. So now we need to repeat that. When I do this fastly, I do this mistake. So in your case, you don't have the excuse. Because you are sitting at home and you drink a coffee, you can do this easily. So, in the PC board, sorry. Yeah. Oh, we are in. Yeah. So now DLE, oil density, So, I have been to this, we found that when we include only this, we could achieve 5 or 6%, and this is increased, like they are rebased to each other. When you improve this, this one can get worse. So for those, it's okay. For viscosity, we always deal with it in a separated step or last step. So viscosity, we use the same technique about viscosity. So now we have a problem only here. So now you can have different choices. Either you increase your range, and we will try that now, or you include omega A and omega B, or you try any other procedure. That will bring us to the equation of state, where, if you remember, when we, okay, let's show the,
I remember from this calculation.
yeah, I think which one is, I think this one, and this. It's just a number where you change it to improve your matching. And you go back to the equation of state to see that. So now I will try again with this model, with the same one, and maybe I increase the range to 3. So I choose wider range. However, this product, this thing should be your last choice. I remember that last year we could achieve the match without changing this. So maybe, yeah, maybe it's better to try with another way. Just skip this. Okay. Maybe we include omega. Okay. You are happy with including omega. So now we have more parameters to control our equation of state, and we will see, is that better than without omega A and B? So you see that your results still improve. So the process or the tuning process is more complicated now. It takes longer time. So to achieve better results, you have to wait this. Maybe you increase also the number of iterations. It's 200. Now maybe you make it 1,000. Then you have to go to sleep, and don't wait this because maybe it takes long time. So I don't have time to wait this. Yeah. And you will repeat this. You will repeat this. At the last step. So at the last step, you will, when you achieve the match with all of them, you still have DLE viscosity. You remember that we say this is matched separately. So after matching all of this, you will go back to this viscosity and match it again, and then calculate average absolute of error for all of them. Yeah, it's okay. If it's not changed, it's okay. If you want to improve it, maybe you include it in your tuning. But you do that separately. So after you do that, different times you achieve your test results, then your model is finished. So now you have prepared a PVT model for your data. How I can use this model? So this is the last step here. When you finish all of this, you go to File and Export. What this means, when you export, you will export a PVT file which is describing the PVT properties for your fluid for different softwares. if you are talking from about Eclipse flat oil, we use this one. So this is PVT modeling. You will build a model based on your equation of state, and from that model you will export the data that can be used in different softwares. So now in Eclipse simulation, where you simulate the reservoir, you will need to include only one file to describe all the PVT behavior or properties. So this is your choice. If you are dealing with flat oil model, if you deal with compositional model, which is important in the case of gas condensate reservoirs, then you will need to export the file with this choice, and so on with the MPAL, CMG, and so on. So now you have prepared a very important part for your simulation model. This is how you describe the oil or gas oil properties mainly, or gas condensate properties. So when you press this one and do that correctly with other previews as here, then you finish it with this software. And what we usually do here in our training, we try to. So this is easy. Just choose your model, and there's different choices. You choose again which one of those. So the last one, and you choose which types of keywords that is used in your simulation model. If you deal with Eclipse, then you will understand what's PVTO and what's PVTG. So this is the keyword which you use it to describe light oil, or oil contains gas. So here we already finished with PVT modeling, but as I said, we need to perform step C, which I think should be your exercise, because this process is already described in your manual here. So you will take the data from DLE and you will calculate beta O. So you have to differentiate in DLE. This is not clear. In DLE, we have beta O and we have GOR or RS. It's the same. Do you know what's the difference between GOR here in PVT or GOR in production? They are different. GOR in production, you have a Q, G, and Q, O, and then you divide. This is related to your production. This is not a big GOR here. It's not your GOR in the PVT measurements. It's different. However, you will only have the same values here and here if your reservoir is above the bubble point. Then you will not lose a gas, and it will be the same. So we say this is GOR production, something like this. So when you read PVT books, don't understand GOR as GOR production. It's different. This is measured in lab, and this is measured in a real reservoir at wellhead. Depends on your production. So this is different. Now we are talking about GOR, which is called, I'm not sure, solution or something like this. Solution, yeah. Because all of the gas, it was dissolved in the oil. But here, all the gas comes together. It's like either dissolved or not, I don't care. I just measure how much gas and how much oil. But here, we're talking about the dissolved gas, which comes out from the oil. So this is the same RS. So we understand this. All of you know what's RS. But you see that in PVT books, they mention RS as GOR. Don't misunderstand this. It's not the same produced GOR or GOR production. So we call this, for DLE measurement, we call this beta O D, which is differential. So it's beta O, but for the differential test. This is also RS D for the differential test. In separator, we call this beta O is for separator and B for the bubble point. And RS also is for separator and P for the bubble point. And those ones, or sometimes not separator, sometimes flash. So they are the same. And this one is exactly the beta O and RS that we will use in our, for example, material balance calculations. So, however, this is only one point. This will be fixed according to beta O that you have from differential liberation. And also this is one value will be fixed according to the value obtained here and here. So to perform this procedure is already clarified here in step by step. We usually do this for the PVT data. You do this for this data. This report, you will take the data from here, and at the end you will, it's not clarified here. They just provide you with the PVT data, but what's the beta function for my data, for PVT data? This is provided here. At the end you will see there's, from Tariq Ahmed, separator test, and how you perform this adjustment. So here's the adjustment, and then he will show you how it should look like at the end. And this is the formula for PVT data. So this is the adjusted. It's lower, usually lower for beta O, and for the RS. So the adjustment, we adjust this data to have these values for the PVT measurement. Don't be misguided or confused by the note here. The note here, it says you need to perform these calculations based on your equation of state, not with the data from the PVT report. This is just for the exercise, but you need to cross out all of this and to understand that this correction is done for PVT data. And I think if it happened already with the first projects with Y function. Some students still confused what's Y function so far. They cannot understand really because we make the exercise reverse. So I think the students will try to practice exactly what we have taken. So maybe if we do this in the lecture, maybe they will memorize it like this, and then maybe they will say you need to correct your data for equation of state, not for the. So remember, this adjustment is done for PVT data, not for the equation of state model. And in your third project, we will ask you to adjust your PVT data. So you will have a PVT data, and you will take the data from the PVT report and calculate the RS and beta O, adjust it. If someone say, okay, I will adjust beta O and RS and start taking data from here. This is from the equation of state. So here he takes the, for example, RS from here and beta O from here. This is from your equation of state. You should not take them from here. If you want the lab data, they are here or in the Excel sheet. So you come to this and you take this data. This is the lab data. Yeah, last point for today. It's about Y function. We said that we always start by evaluating our data. Y function is the point where you start evaluate your data. In your term project, if you were asked to evaluate your CCE data, it means you start by Y function And from Y function, you will tell if the V relative at pressure below saturation pressure is okay or not. How you know that? Because in Y function we plot a straight line with several points. And if these points like this in the straight line, it means like you are in the okay case. If your points like this, and then it's not okay. And however, we will recalculate the V relative volume from Y function, and then we can calculate the average absolute error, and it should be also less than 1%. So the first step, you get data, you get CCE measurement, and you start by Y function to evaluate your CCE data, which is relative volume, at pressure below saturation pressure. That's where we calculate Y function. And that's it for today. Sorry for making you wait.